Welcome back to the final keynote session of the Python Web Conference 2020. I am super excited. This has been an amazing 3 days, but it's not done yet. We still have one more amazing speaker this afternoon for us. So if you all are sitting down and ready to go, I've got Steve Flanders here from Splunk, who's going to talk to us about Python Web and observability. Steve, I'll let you take it away.
Perfect. Thank you so much. Glad to be here, and hopefully you enjoy this talk. So as kind of mentioned, the goal is to talk about Python Web in the context of observability. I'm going to do this in a variety of different ways. So basically talk about how Python web apps are kind of evolving now, how the landscape of developing as a whole is kind of moving to more of a distributed microservices-based model. What observability means and how it's different from, say, traditional monitoring that you're probably familiar with, what that means specifically for Python web applications, kind of the power of distributed tracing, which is a part of observability that's super critical that most people may not be paying as much attention to, but especially as you start moving to more distributed architectures, it's super important. And then what does it mean for the Python web community as a whole, as well as what does it mean for you, whether that is an engineer that's building Python web applications or maybe contributing to Python libraries and the like. So my name is Steve Flanders. I'm a director of engineering at Splunk. I've kind of been in the monitoring observability space here for about a decade, focused a lot on the logging space, now more on the distributed tracing side, really working on anything in kind of open source or open standards based observability. So let's start by talking a bit about Python web applications. And really on the surface, it's quite simple, right? I mean, you have a single user probably talks to a single one of your Python web applications, and that probably just talks to a single database. I mean, how much harder could it possibly be? Except that's not the world that we live in. Any real Python web application that's being used in a production environment or at scale is way more complex than that. It's actually likely fully distributed in order to handle both the customer demand, the availability requirements, the resiliency that you want to have, different scenarios around DR and the like. So we're talking about many users, hundreds, maybe thousands of users that are hitting our application. And that application, of course, needs to scale out. So there's a load balancer in front of it. For availability or even performance reasons, you may have deployed this web application in multiple different regions. And as you start scaling the app, you're probably looking at a microservices-based architecture. That's where a lot of them are going today. And so you're not talking to like one backend, or you don't have all the logic within your Python web application itself. You're actually calling out to a variety of different services that specialize in a certain subset of functionality, depending on what your web application is doing. Like if you're doing some sort of like e-commerce type thing, then you need to handle like carts and checking out and payment information. You probably have advertisements and the like. And each of those different operations or functions probably represents a different backend microservice that you need to call into. Now, each of these backend services they probably have their own dedicated database. There's probably even a caching tier between the backend and the database for performance reasons. Or they may even call out to other third-party services. Maybe you don't want to handle advertisements yourself, so you've off-sourced that to like a third party. And so you have a backend service that actually communicates with it, which means maybe it doesn't have its own persistence layer. It's calling out to another dependency. The net result of this is the environment is it's super complex. And you actually see this through different Python web frameworks that are out there, their ability of kind of going synchronous versus asynchronous. Maybe you're talking to message buses and the like, and you really need to handle this distributed nature, which isn't quite as simple as it may seem. And not only is it distributed, but it's probably getting more and more complex, especially as you start scaling up and really handling like production class traffic. If you actually look at microservices architectures as a whole, they're made up of many different components, and their characteristics are very different than typical monolithic architectures that we came from in the previous generation. I mean, as you can see here, I really like this chart from microservices.io, but if you think about this at a high level, things like the way that you deploy microservices matter. Like maybe there's an order to the way things come up or how they scale out. Service discovery is pretty important because you need to figure out who you're talking to and what that actually looks like. Circuit breaking becomes important because you don't want your system to collapse because of a certain usage pattern or maybe a mal user that's causing issues to your environment. One of the key aspects that is applicable to microservices architecture that I'm going to drill into here in just a little bit is really around observability. And observability is made up of many different components, and you're probably using some of them today, but how do you tie it all together in order to get visibility and be able to answer questions in your environment is a pretty interesting question, whether it's a Python web app or really any microservices app, and we'll drill more into that. Now, not only is it distributed and complex, it's also really quite challenging to maintain a production environment at scale. And Python web applications are no exception to this. This is actually a survey that the CNCF, or Cloud Native Compute Foundation, ran. And one thing that stands out every single time they run this survey is that of like the top 10 issues that happen, 4 or 5 of them are in the monitoring or observability or logging or reliability space. And this really calls out that like these are super important problems that need to be solved in order to ensure that your application is successful. And they're probably outside of like the core IP that you care about when you're building your Python web application. Like you want your application to perform the function it was built to, but you have to also realize that it may not be used the way that you anticipated it, or some unknown errors or issues may unfold, and you're going to need to troubleshoot quickly in order to get the application working the way that you expect it to, or maybe your customers expect. So this kind of calls out that the world that we're moving to allows us to scale, allows us often to move faster, allows us to be more agile and kind of meet customer needs, but it also has some side effects or some potential consequences that we need to be aware of, like how are we going to monitor and observe this system? How are we going to get it back online? How are we going to make sure that our availability and performance concerns are being addressed in a timely manner while we continue to execute against making the best web application that we possibly can? So with that kind of context as to the problem space we look at, especially as we move it to more modern applications, I want to drill a bit into observability and what it is. Now, you may have heard this term before, and some people kind of think, well, hey, it's just a fancy word for monitoring, but it's actually not. It has a pretty significant difference. And many people have kind of tried to explain it. I like this quote from Baron that talks about how monitoring, it basically tells you how the system is behaving because you have configured it based on things that you know indicate problems. Usually this is past experience or maybe best practices, but it's known ahead of time that if the system behaves this way, you should be notified about it so you can go fix it. Observability is actually the opposite. The observability is all about being able to ask any question about your environment in order to determine why it's not working. And in order to ask any question, we're talking about unknowns here. So you can't ahead of time prepare or try to change the telemetry or even easily reproduce the problem. You need to be able to do like live debugging and be able to really pinpoint problems quickly. Observability looks to solve that in the types of data that it's collecting, and then the way that you kind of analyze it in the back end or back ends of your choice, you're actually leveraging to query that data back out and get real insights. So let's drill a bit more into observability. Another fancy phrase that you may have heard is about the 3 pillars of observability. This is very common. Basically, you should think of them as different data sources. So like logs, metrics, and traces are the more traditional ways that you would monitor your environment. And together they can all serve to help really provide observability. But on the surface, they're just data sources. They don't inherently, like if you collect all 3, you don't have observability. But you have some data that could be used to get to an observability solution. Now, each of these different data sources, they have some similarities. So for example, they're all kind of time related, so you can know when they occurred, and they all provide some amount of metadata. So they may provide like infrastructure correlation or have some amount of business logic as to what is happening, or just some known like semantic conventions as to how things are defined in your environment. But the data sources themselves, or the data that's actually being emitted from each of these data sources, is different. So for example, in logs, more traditionally it would be unstructured text, but it's starting to move to more of a structured format in general. You have metrics, which is really around data points and being more numeric in nature. And then you have tracing, which is more end-to-end requests through your system. And what does that actually mean? And some amount of metrics can actually be deduced from traces because they offer red metrics or requests, errors, and duration information that can really help you troubleshoot some of your environmental needs. Now, while there are similarities and you can see the data themselves are different, the way in which they are used are also very different. So traditionally, logs were for the last mile analysis. Like you've already done problem isolation. Now you want to know like what is the root cause? Why did this happen? How can I prevent it in the future? What was the indication of the change that happened in my environment? It's really the end of the road is where logs often have the most value, primarily because if they're unstructured and you need to query over them, it's like trying to find a needle in the haystack. So unless you can really refine your query capabilities to a subset of logs, it can be a little nuanced in order to get the data out that you care about. Metrics on the other side of the house are really used to alert about a problem. I actually like to think of them more as symptoms. They indicate kind of general behaviors or even health of your environment, but they don't really tell you why something happened. They tell you that something happened. And then it's up to you to figure out, like, is that a real indication of a problem or a red herring or not? Also, they don't have context and correlation. So especially as you look at more distributed architectures, symptoms can happen anywhere. And so you can actually end up with alert storms if you're not careful about how you define them. And then traces, they really help with problem isolation, especially in distributed architectures. The idea is if I have multiple microservices that talk to each other and they have complex relationships that may even change over time, like if I build, I don't know, an ad service, it's possible that multiple different teams at my company could be relying on that ad service for different products or use cases. And those products and use cases can change over time, so the demands of the ad service can change over time. But one of the interesting things that traces provides is context and correlation. So you can use that to actually indicate where errors originated from, for example, and actually start to isolate the problem, especially if you have enriched trace data with metadata. So for example, maybe I can determine if this is happening in a certain region or only for a certain build of the service or any other really dimension or other metadata that might be associated with the traces themselves. So these data sources are very valuable, but it's what you do with them and how you actually leverage the power that they provide that gives you the actual observability. So it's more about the back end that you're using and your ability to query that data out quickly and get insights about what is happening in your environment. So let's talk a little bit about the current state of Python web observability. I would say there are similarly about 3 pillars, but the pillars are slightly different and the way that they're leveraged is different. So logging predominantly is used kind of end to end. Like most people today, we're probably adding some amount of logging to the Python web application. It gives them some pretty quick insights on whether or not there's a problem happening or like perhaps state or configuration changes in the system. Luckily, it's pretty easy. Like there's a common import logging library that you can leverage, or there are wrappers around it to provide enhanced capabilities, but there's kind of a standard, if you will, for how you get logging out of your Python web applications. Metrics on the other side, not as common. I mean, they exist to some extent, but there's no real standard here. I mean, I guess it's kind of moving in the Prometheus direction. So Prometheus is an open source kind of way of getting metrics out of not just Python, really any language. And it's becoming a pretty common standard in the industry today to do it. The alternative, or even prior, was more proprietary in nature, like you had to have a vendor solution for how you'd collect these metrics. Or you might have had an open source solution, but some of them are kind of dying off at this point, like collectd, some amount of statsd, maybe plugging into Graphite or something else. But there wasn't really any commonality around it. And even if you look at Python web frameworks, there's no real consistency there either. There's some amount of options available to you, but you have to kind of figure that out and navigate it yourself. And then the third pillar is actually a little bit different. It's about errors. And you might think of this as glorified logging, but it is trying to solve a particular problem. And that is a data source that's really, it's usually exception-based tracking. So some sort of stack of what happened or the execution path of it and the error that came out of the calls that were being made. You might think of Sentry, for example, as something that provides this amount of insights from errors that are generated. But it's really just about exceptions, and it's really just glorified logging. You might even just call it logs and not even call it out separately. I like to call it out separately because it's pretty common you're going to send your logs to one backend and your error or exceptions to a different one, just like you would send metrics to a third one. So calling out as a different kind of data source, I think is important as you think about how you're perhaps instrumenting or leveraging the telemetry data that you're emitting from your applications. Now, if we look across these three different data sources, logs are pretty hard to use. I mean, if you know what you're looking for, or if you have the time to query over it, or if you really invested in making those logs structured, maybe you can do it. But they're usually quite verbose, and it can be a lot of data, so querying can be complex and may even require a fair amount of regex experience in order to get the insights that you care about. Metrics, they are very helpful in indicating symptoms, and if they're configured properly, can be used for alerts, though you have to be careful of alert storms. But they're symptoms, they're not root cause. So they don't typically help with problem isolation, and they don't typically get down to the why this symptom is occurring type of thing. Errors, on the other hand, are typically very exception-based, as I mentioned, and they may get you to root cause, but I mean, exceptions could happen anywhere in a stack, and especially in microservices applications, it's not uncommon that errors could happen in multiple microservices at the same time for a given call. Even if you do get to a root cause, getting to the actual impact of that root cause is not typically possible with just looking at the error conventions that are available today. So you can try to go fix it, but if you're having 2 or 3 of them in your environment at once, knowing which one to prioritize, looking at just the errors alone is typically not that possible. So this is where I want to talk a bit about distributed tracing and the importance of distributed tracing. First off, it's not as common today in Python web applications. It's not very common in monolithic applications. Maybe you've heard of APM or application performance monitoring, but as you move to more distributed microservices, it becomes super important. And while most people add some amount of logging or metrics today, if they're moving to or building microservices, they may not be thinking about distributed tracing. And that can cause problems down the line based on the complexity of distributed based architectures. So what is distributed tracing? Well, I took this infographic from Jaeger Tracing. So Jaeger is a open source, basically client library, data collection and backend for distributed tracing data. It came out of Uber. And on the left here, you basically have a representation of a call tree. So you can think of basically every circle being a different service in your environment. So like a microservices-based architecture and different call paths that can happen in this tree. And the important thing about distributed tracing is that you're passing context between your calls. So for example, this is typically called a trace ID. It's an identifier that uniquely identifies a given request through all the different calls that it makes in your architecture. And so as those calls are made across service tiers, so service to service, that context is actually passed down with it. This is typically done, like if you're thinking of RESTful-based services, we're talking about context propagation through headers. So some sort of header format is used, and you use the same context propagation format for all of your microservices. So for example, B3 headers are very common, or there's a new standard that's emerging right now from W3C called trace context. But basically the idea here is a uniquely way of identifying end-to-end that context is passed. A service would have to actually be able to pick up that context if it is passed in a request that's being made, or create that context if it's a new request and nothing is being passed the initial call, and be able to pass that down if additional calls downstream are occurring as well. The net result is what happens on the right-hand side, which is kind of a waterfall view of what that request looks like. So A would be like the parent level trace representation, so how long the entire request took. then maybe like B and E here would represent different microservices. So for example, the B microservice is called first, some things happen, and then the E microservice is called. But within a microservice, you may actually have like functional level instrumentation. That would be kind of what C and D represent here. So I come into a microservice, I do some things, multiple different calls occur. Each of those generate what are called spans. And so spans, multiple of them can happen in a given microservice, or spans can happen when one microservice calls another one. Now, from here, because I know how long it took based on all the spans that I'm gathering in the context that I pass, that basically gives me duration-based information for every single call as well as for the entire request. If errors occur, those can also be identified here. In fact, you can determine where an error originated from versus where it propagated through a call path or through a request path in your environment. And then the number of requests, again, this information can be gathered by the trace and span data that's available. So why would you use distributed tracing information? Three primary use cases come to mind here. First, availability. So if you want to ensure that your system is up and working the way that it should be, identifying kind of errors that are occurring or services that are down, that can totally happen with distributed tracing because you have that context. You can even get to problem isolation pretty quickly because you know where an error originated from or where things might be taking more time than are anticipated. Another more common one, especially if you're looking at like the APM or application performance monitoring space, would be performance in general. Like, is a call slow? Is a microservice slow? Does my database need to be optimized? These typically are things that you would fix, and then hopefully that problem goes away for some period of time. You may have multiple performance bottlenecks in your system, so maybe you have to go through a variety of different fixes. You fix one thing, and then performance changes in a different aspect of your environment. But this is more for service owners. It can also impact potentially customer experience if people are complaining about the performance of your Python web application. And then the final primary use case would be more around testing. Like maybe I'm doing a canary deploy and I want to know whether the performance or even availability characteristics are better or worse as a result of this new build. All of this is possible because of two primary reasons. One, we have context, and second, we have some amount of metadata that can be used to enrich the data that we're generating with distributed traces. Now, in order to get distributed tracing information, you have to actually instrument your application. This is no different than adding logging. This is no different than adding metrics. The question is, how much overhead is it for a Python developer to add it to their application? There are actually a variety of open source solutions that are out there today. Everything on this slide is open source and available. They offer different things depending on what you're looking for. For example, some are only trace specific. They won't help you with metrics. Some offer a combination of things. It really depends on what you're looking for. In general, the industry is starting to move to a standard called OpenTelemetry. This is a newer project. But it's actually the merging of two other projects, being Open Tracing and Open Census, the two that are in the middle here. That's the logos for them. Basically, the idea is to make it really easy to instrument your application for any data source. The primary focus has been around tracing. Metrics is starting to wrap up right now, and logs is just kicking off. And also offers kind of an end-to-end implementation for you, which includes data collection mechanisms. I'll show a bit of that in a minute. But this is a way of basically taking a dependency, perhaps manipulating your code to actually add the instrumentation that you care about, and then having that telemetry data be exposed to a backend or multiple backends, depending on your use cases. Now, I do want to call out that instrumentation is not as easy as it may sound, no matter which data source you are talking about. Some people may not be aware of all the nuances here. They're actually super important. Like for each of the verticals, whether it's tracing or metrics or logs, everything you're doing has multiple implications, both being like, here we're talking about Python, it's language specific. If I do something for Python, that doesn't mean that Java gets it for free, right? And vice versa. So especially with the instrumentation, it's very language specific. The APIs that you're consuming, the end-to-end implementation, the client library information itself. You then can offload this to like an agent or collection type mechanism, and that can be more centralized. It's no longer language specific, it's an implementation, and you end up sending to it in one or more different formats. And then those interop formats are actually important as well. I mentioned context propagation a little bit earlier. B3 to W3C is a great example of different standards that are out there in order to get a certain telemetry thing to work for you. This is a pretty complex space, and depending on the open source or vendor specific implementation you're using, you get different levels of maturity and even adoption. I did forget to call out on the previous slide, in addition to the open source options that are out there, there are actually plenty of vendor specific solutions as well. The problem with the vendor specific solutions are that they're vendor specific, which means they kind of lock you in, and the open source solutions are really trying to give you more flexibility. So it's not about how you instrument, it's more about how you use that data that you're collecting. So you can go choose a commercial backend if you want, or multiple, and hopefully switch pretty easily without having to go touch your app. Because these instrumentation things, some of them can be invasive. If you're doing manual instrumentation, you're modifying your code, which you then need to go test, and you need to go put through your CI/CD pipeline and go get into production and make sure it's properly like hardened. You don't want to make a lot of changes there. That's probably not where your core IP is. You want to be building your Python web app, right? And not really focusing about the telemetry data. You just want to be able to leverage it when you run into problems. So for these different cloud native telemetry things, OpenTelemetry as a whole is trying to solve this. Most of the other solutions out there, like Jaeger, cares really about tracing. Prometheus cares really about metrics. Elastic cares really about logs, though Elastic is kind of getting more broad into some amount of tracing and metrics as well. So there's many options out there. This is an open source CNCF project that's worth taking a look at. So now let's talk about Python instrumentation and how you would actually do it with a real app. I'm going to leverage OpenTelemetry as an example of how you can get started with this, but I mean, it would be very similar if you're using Jaeger or Zipkin. Commercial or more proprietary vendor-specific agents might be a bit different, but they should follow kind of similar guidelines and practices here. So let's say I have a Python web application. It has a bunch of requirements or dependencies I want to go ahead and install. I do that. If I want to take advantage of some sort of client library that will help me instrument my application, I'd have to install those dependencies as well. In the case of OpenTelemetry, it's actually pretty granular, and so you can kind of pick and choose the aspects that are applicable to you. The API and SDK give you the actual Python implementation of OpenTelemetry's instrumentation and all the framework that you need to like handle the context propagation, to handle the ability of generating traces and spans and kind of passing that around through your application, as well as tacking on the metadata that you care about. The instrumentation dependency actually can help auto instrument your app. And I'm going to demonstrate what the difference is between auto and manual here in just a second. And then everything else is really extension based. What libraries am I using? So here you can see, like, I'm going to show a demo with a Flask application. If you're using Django or something else, Tornado, like you would install the appropriate extensions for the frameworks or libraries that you're leveraging. If you have multiple different dependencies, maybe you're calling out to databases, those are additional extensions that you add. And then the only other thing here that may not be familiar is this OTLP thing. You have to basically export your telemetry in some sort of format. OpenTelemetry has a format called OTLP. You could replace that with Jaeger or Zipkin or whatever you're using to actually get the data to the backend that you care about. So here you can see the yellow command is what I would typically run to fire up my Python web application. And everything in white are kind of the changes that are going to be necessary in order to get instrumentation into my app. So first up, install the dependencies that I care about. Next up, I'm going to talk about auto instrumentation first. So one thing that some client libraries offer, I would say the industry as a whole, like vendors, some vendors offer auto instrumentation. In the open source, most of it's manual. There's some amount of auto, but it's not as feature rich today. OpenTelemetry is actually moving to a model of offering all auto based. Java is probably the furthest along. Python and Node are catching up, and then some of the other languages are not complete yet. The basic idea here is, in a perfect world, you don't have to modify any of your application code to get instrumentation out. That's the nirvana state that you're trying to get into. Today in OpenTelemetry, you do have to make a little bit of code modification because it hasn't been abstracted out. Like I can't configure an exporter today, so I can't send out OTOP, for example, without modifying my app. There is an issue open. The goal is to fix this. It will be coming soon. But for the purposes of this demo, I'll show you how you'd modify your code to get the auto instrumentation aspect. So let's say I have a Python application app.py. Here's basically a diff of here's my application and here's my application once I add the auto instrumentation hook. Basically, all I have to do is add the exporter that I care about, and then the ability to import and export spans through a tracer. So that's basically the code chunk that's being added right now. In the future, this code chunk will not be required. It will literally be no code changes whatsoever. And then what we do is we wrap the Python call with the OpenTelemetry instrument command. This is what auto instruments the application. And so it's basically a runtime parameter. The dependencies plus the runtime parameter will lead to the instrumentation for me automatically, or soon to be automatically, given that this configuration parameter requires a little bit of change. Once I do this and I run my application, I will start seeing telemetry data being emitted for my entire Flask application. So request information that's happening, get, post, HTTP status codes, the URLs, the different servers I'm calling to. Even in this case, you'll see like SQLite, so calling out to the SQL database. All of that will automatically happen with no other code changes, no other functional level changes whatsoever. And again, I will demo this here in just a second. The alternative is if I wanted to manually instrument my app, I would have to go in and make actual code changes to, let's say, my functions around the routes that I have for my Flask application. So on the right-hand side here, I have an example of the additional changes beyond the auto instrumentation changes to add manual instrumentation. And as you can see, I mean, it's a very basic example, calling a single route, and it's just returning a single string. There's a fair amount of boilerplate I need to add in here, right? I need to add the context propagation information. I may need to add my own key value pairs. They're called attributes in OpenTelemetry, but basically the metadata that I care about. So here I'm setting like a span kind to server, and then I need to actually get the other information, like maybe the parameters that are being called in the request, and pass that in through my span information. It's pretty heavyweight to add manual instrumentation, but it's also very flexible. Like as a developer, I can decide what to instrument and not instrument, how rich I want it to be, what metadata I want it to contain. Really, I control all the telemetry data that's coming out of the system. With auto instrumentation, it's less work on the developer. Like you just kind of get it for free, but you also have less control. Like in the case of Flask, all the routes are going to be instrumented. I can't really select which ones are or are not unless I want to add manual instrumentation myself. The amount of metadata, there's some that come out for free. I'll talk a little bit about semantic conventions here in a bit, but if I wanted to add my own custom metadata, that's more on me and probably modifying my app to add that in. The other problem with auto instrumentation is that it's library and framework specific. So unless the auto instrumentation supports the library or frameworks you're using, you won't get auto instrumentation for free in most cases. There are some exceptions to that. So if you're using some like obscure library or framework, or maybe a proprietary one that you wrote or something in-house to your company, then you might have to head down the manual route in order to get the data out that you care about. So as you can see here, there's still a fair amount of work that's needed even between auto and manual, but the goal is soon it's dependencies and a runtime command and you're done, which means you don't have to really think about it. As new libraries and frameworks come out, you do have to wait some period of time for that auto instrumentation to exist. Hopefully that'll get smoother over time. The goal is that hopefully this will get pretty broad adoption and then it'll be pretty easy to take advantage of it. With that, I want to jump very quickly here to a demo of how this all works. So I actually have a GitHub repo up. I'll share the link out here. It basically has a setup script. So I'll just go ahead and run that setup script behind the scenes here. What it's going to do is basically fire up a Flask CRUD application, start a virtual environment, and install all the dependencies as well as the SQLite database to make this CRUD application work. On top of that, I mentioned we have to install a bunch of dependencies to make OpenTelemetry work in the case of client library instrumentation. So it'll go ahead and do that. And then I've also fired up a collector and a backend. So I'm using the OpenTelemetry collector, but you could use the Jaeger collector or whatever vendor collector is required for your environment. And then I'm using Jaeger as a backend so I can actually visualize this data. So you can see my Flask application here is running. It's actually running right now uninstrumented. So I've added the dependencies, but I haven't added in the hook to export the data. I can go ahead and fire up this demo application. I can just type in some sort of example code here and save it. I can actually do some different operations, even delete it. What that actually does is it makes a bunch of requests in my system, but you'll notice no telemetry data is being emitted because it's not an instrumented app. It's just a Python web app that I wrote, or actually someone else wrote in this case. So pretty easy to get started. Now what we'll do is add in the hook of the code to export that data, like I showed on the slide previously, and then restart the application. So the app is running here again. I can do a second example, example 2 here, save that in, again, run some commands. And what you'll notice now is it's actually emitting telemetry data. So I've actually configured it to export to the console as well as send to Jaeger in this case. But you can see there's trace information here, there's span information, that server kind span we talked about earlier, there's method information. So without modifying my app other than to add the exporter, I'm getting a whole bunch of Flask information being emitted from my system. And I can fire up Jaeger here. I can go look at some of the spans being generated, and you can see like HTTP requests that are coming in, methods that are being called, the endpoints and ports, even the span format that I'm using. So rich metadata that I can use to kind of slice and dice that information, as well as any other calls that it makes. So in this case, like calling the web server actually calls the SQLite database. Even in the case of the database, I can see the DB query that was run because that's being instrumented as well for me automatically. So a lot of flexibility here with little overhead to the end user on how to get this telemetry data out. This example is up and running. Folks can go take a look at it after the session. I'll share the link here on the last slide. But as you can see, it's not a lot of work to get started, but you do need to think about it. And especially if you're going to operate a Python web service in production, you need to think through like the metadata, what you're collecting, different sampling policies. There are some decisions around how you handle the telemetry data that you're emitting from your system. Okay, I did mention a few times this notion of semantic conventions. So as you're instrumenting your app, ideally you're doing it in a standard way. We usually call these open standards or semantic conventions. Like for example, in the case of RESTful services, things like the method and the status code and the URL are super important. And in general, the industry is getting around different standards. Like open tracing has some, OpenSymmetry is forming the next generation of these. But here's an example of like a key name that you would have. And then you have your associated values, like method would be get or post or whatever. Status code could be the numeric value of it, for example. So that's kind of RESTful based. You can do the same thing for gRPC. You can have errors. So we talked about like how things like Sentry work. Same thing in distributed tracing. You want to know whether an error occurred, which service it happened in the case of like a stack or some sort of error message, how you want to capture that so you can actually represent it in the backend or backends of your choice. And then even calls out to like third-party systems. Like maybe you're using a database from a cloud provider or you're paying a third party. You don't have the ability to go instrument the database that you're calling, but you still want to see distributed trace information to it. You can actually do that with distributed tracing as well. That's span kind equals server. There's also a span kind equals client, which means my instrumented Python web app is calling a database. That database isn't instrumented, but I know when I make a call to it and I can report that span information and any errors and things that come back to me. So sometimes this is called like an inferred service. You have a way of kind of inferring things, even if they're not instrumented, as long as they're kind of at the end of the chain. Like if they happen in the middle, that would cause a bit of an issue because you would lose visibility. You wouldn't be able to stitch all the context between. Okay, so let's talk about next steps here. We talked about Python web apps, we talked about microservices, the complexity of it. We talked about observability, how things like distributed tracing can help, the different types of instrumentation you need to think about, and how like the focus needs to be not just logs and metrics, but also kind of this tracing world. what does it mean for you? And I know that there are many different yous out there. So maybe you as a Python library or framework maintainer or writer, could be you as a Python web engineer. It could be you as a DevOps or SRE type that's responsible for ensuring that this Python web app works. I think there's a few key takeaways here, or even calls to action, if you will. One would be you need to think about and really plan for observability. It's not just about getting data sources and getting that information out. It's about what data are you collecting? How are you collecting? How does it impact the system? How are you going to analyze it? Can you really ask any question of your data? If not, what do you need to change? What do you need to plan for? What do you need to work with your developers in order to add that visibility? Next is around leveraging open source and open standards-based instrumentation. One of the big things that I'm seeing is that everything from instrumentation and data collection is moving to open source and open standards. It's very much moving away from vendor implementations. Vendor implementations are great, but they lead you to some amount of lock-in. As things like OpenTelemetry kind of take off, it really opens the door of instrumenting once or collecting data once, and then the backends are where you differentiate. And as long as they adhere to and follow the semantic conventions that are out there, you kind of just get the power of whatever the backend is. Maybe it's the streaming or real-time aspects, maybe it's its scalability options, maybe it's the way it visualizes the data for you. There's a variety of reasons why you might leverage a backend, whether it's open source or commercial, or maybe even multiple backends depending on your use cases. Be sure to enrich your data with metadata. So sure, like in the case of distributed tracing, you get red metrics for free, but things like what region is this thing running in? What's its build version number? Maybe in the case of I mean, some of these are language specific, but like even things like garbage collection metrics could actually be tacked into span information. So the more that you enrich, the more questions you can ask of your data. You probably will enrich based on known areas of problems that you have in your environment. Maybe in your environment, it's more common that apps are impacted because of the infrastructure. So you want to add more infrastructure metadata. Maybe it's because of build or CI/CD things. You want to have more rich build information added. Whatever is applicable to you. And there are kind of some best practices on what to add. And then finally, ensure that the data you're collecting is actually valuable. Like you don't want to waste money consuming all these resources for things that you either can't easily get the data out of, or doesn't actually give you the ability of asking any question of your data and getting real insights, getting to problem isolation, getting to root cause, and really making sure your business and your Python web app is working the way that you expect it. So those are kind of some of the big things I would look at. It doesn't matter whether you're using synchronous or asynchronous. It doesn't matter whether you have message buses or queues, and whether you're doing batch processing or not. All of these things can be instrumented. It's all about passing that context around, understanding what questions you want to ask about your web application or anything you're calling to, and how you can really gain insights from them. With that, thank you so much for having me. I really appreciate it. As I mentioned, here's a link to GitHub that kind of shows off the demo that I just showed, as well as a link to the OpenTelemetry Python project. There are plenty others out there as well, and I'll be available even after this session for questions if people have them. Thank you.
That is awesome. Thank you so much, Steve, for being here with us. I love all the open source tools that are available, and you've opened my eyes to some new stuff I need to go check out. So this has been great. So if folks want to actually ask Steve questions in person, like face-to-face, feel free to join in the gallery link below. He'll be there in a Zoom meeting, like a regular old Zoom meeting, and you can interact with him. But make sure you hang around. At the top of the hour, we will have the closing remarks, and you won't want to miss that because it's going to be a lot of fun. If I can make it through that without shedding a tear and crying in happiness, we'll see if that works. But I really want to thank you again, Steve, for being a speaker here. We can't do these kinds of conferences without having amazing speakers like you available and spending and dedicating so much time to our group and being here with us.
Thanks so much for having me.
Yeah, great. All right, so everybody else, we will see you at the top of the hour. So that will be 5 o'clock Eastern Daylight Time, and we will do the closing remarks right back here. If you missed the beginning of this talk, don't worry. The recording will be up momentarily, probably in about next 10 to 20 minutes. You'll be able to actually watch this talk from the very beginning right on the platform. So we'll see you all soon. Join us back here for closings. Thanks, Steve.